Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about popular discrete distributions. We already talked about discrete random variables in the previous video, and we explained that when we manipulate discrete random variables, we do it through their probability mass function. So when we have some data and we want to model it as a discrete random variable, what we do is we use the data to estimate the probability mass function. Here is an example. If you remember, it has to do with free throws in basketball, but it doesn't really matter. So if we're interested in the probability that the random variable has a certain value like 10, what we're going to do is we're going to look at the data and see, how many data points have value 10 out of the total number of data points? And in this case, it's about 4%, if that's the number that corresponds to 10. And what happens when we do this, we're going to see later on that this is called a non-parametric estimator of the PMF. We're going to talk a lot more about that. The point is that when we use the empirical PMF, the estimate can be very noisy. This kind of looks quite noisy. We'll talk, again, a lot more about that later on, but the point is that it does look pretty noisy, and we already discussed that even if we knew the true underlying model, when we look at the empirical PMF, it can look quite different, especially if you have limited data. In order to address this in some situations, it's a good idea to exploit the information that you have about the phenomenon that you're trying to model to come up with a predefined shape for the PMF that can depend on a small number of parameters. Okay, that's called parametric modeling, and that's our motivation today. We want to design some discrete distributions, which is equivalent to saying that we want to design some probability mass functions that incorporate certain assumptions that can occur often in practice and which will allow us to model this kind of data more efficiently. We'll talk about that aspect later on. Today we're going to focus on designing these probability mass functions, which correspond to famous distributions such as the geometric, the binomial, and the Poisson distributions. Okay, so the goal here is going to be to derive several very popular discrete distributions. The prerequisites are the definition of probability, independence, and of course, the definition of discrete random variables. Let's start with the simplest possible distribution that you could imagine, the Bernoulli distribution, which models situations where we have two possible results. For example, a coin flip that can be heads or tails, and the probability of one of the results we say is theta, which is going to be the parameter that we can tweak to fit the distribution later on if we see some data. But for now we're going to basically assume that these parameters, just to be clear, what we're going to do is we're going to be deriving probability mass functions that depend on a small number of parameters. In this case, a single parameter theta. And we're just going to leave the function as a function of, the probability mass function, the PMF, we want to leave it as a function of the parameter. And then we will explain how to set that parameter using data in the next video. Okay? Here, if we have a Bernoulli random variable with parameter theta, the probability of the PMF at 1, is the probability that we get this first result, heads, for example, in the case of the coin flip, which we assign to 1, that's going to be theta, okay, by definition. So then the probability of 0, of not seeing that particular result, is just 1 minus theta. Okay, so the Bernoulli distribution is as simple as it gets. Probability of 1 is theta, probability of 0 is 1 minus theta. And then to fit this parameter theta to the data, you would observe the data, and we will talk about how to determine the parameter later on. Okay, let's go to a more interesting case. Imagine that I have a coin that has bias theta, meaning that the probability of heads is theta, and I flip it independently n times. What is the probability of getting a head? This is going to allow us to derive a very famous distribution. We're going to follow this strategy. We're going to decompose the event that we're interested in, which is obtaining a heads, into the union of several events. Why are we doing this like that? Well, if I think of, imagine that I'm just flipping the coin 3 times, and I want to see how many, what's the probability that I get 2 heads. The thing is that I can get 2 heads in many different ways, right? So I can get heads, then tails. I can get head, tails, head. I can get tails, head, head. Okay, so when I say I'm going to divide the event that I get A heads into several like sub-events, if you want, this is exactly what I mean. Okay, so in this case, if I was interested in if A was equal to 2, if I was interested in the probability of getting 2 heads, what I would do is, well, what I want to do is I want to separate this into the probability of these 3 sub-events, and then I can add them up because the sub-events are disjoint, right? So the probability of A heads is the probability that I get A heads, you know, the first A coin flips are heads, that the first coin flip is heads, then the second one is tails, and then the next A-1 coin flips are heads, and so on and so forth. Okay, so I'm being a bit lazy. Okay, what I'm saying is I'm going to consider the union of all the possible ways, all the possible orderings in which I would have A heads and n minus A tails. Okay, and those are the sub-events that I'm going to be interested in. Like, a question for you is, are those sub-events disjoint? And the answer is yes, because they cannot happen at the same time, right? I cannot have heads, heads, tails, and heads, tails, heads at the same time. They are obviously disjoint. Okay, so I'm going to be able to sum their probabilities. So now let's focus on how to compute the probabilities of the individual events. So let's, for example, think of the fixed ordering where I have first A heads and then n minus A tails. We've made an assumption that is crucial here, which is that the coin flips are independent. Because the coin flips are independent, we can split this into the product of the probabilities of the individual events. And now we have assumed that every coin flip has the same probability, which is theta. So let me go back for a moment because maybe that was a bit quick. Here we're assuming that the coin flip has probability theta of being heads. That is going to be the parameter of our probability mass function. So what we're doing here is we're deriving the probability that we obtain A heads. That probability is going to depend on theta, which would be the parameter that we would set with the data later on. Okay. So let me get back to it. We had seen that we want to separate into these sub-events because their sum is going to be the event that we're interested in. Now for this one in particular, because of the independence assumption, we can just split this into factorize the probability into the probability of the individual events. And now here we can use this assumption that the probability of heads is always theta and the probability of tails is 1 minus theta. So how many times are we multiplying by theta? 8 times. So we're going to get theta to the A. How many times are we multiplying by 1 minus theta? The number of tails, which is n minus A, we're going to get theta to the n minus A. Okay, so the probability of a fixed ordering of having heads, 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 in this case, 8 times in a row, and then tails, 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 n minus A times in a row is theta to the A, because we're multiplying by theta 8 times 1 minus theta to the n minus A, because we're multiplying 1 minus theta n minus 8 times. Okay? But that only gives us one of the orderings. We need to worry about every other possible ordering. So here, for example, imagine, it was heads, then tails, and then A minus 1 heads, and then n minus A minus 1 tails, so a different ordering. If we apply exactly the same argument, here in the second step, we see that the order doesn't matter at all, right? Because we have a product of all these individual probabilities, it doesn't matter how they ordered. And this is because they're independent, intuitively speaking. So we're going to obtain exactly the same result no matter what ordering, as long as there are A heads and N minus A tails. Okay, so now we know that all of these sub-events that we're interested in, which is like some ordering in which you get A heads and N minus A tails, they all have the same probability. So now we have to ask ourselves how many possible orders are there. And basically the way you can choose A heads out of N slots to put the heads by simple combinatorics is just N choose A. Okay, so it's given by this formula. We're not really going to go into the detail of the combinatorics. You can look up in Wikipedia or wherever, like binomial coefficient, and you will find a justification for this formula. So basically, the probability of getting A heads is the sum of all these sub-events where we get A heads and N minus A tails, and that's this number multiplied by the probability of each of them, which we have seen is the same. So it's this binomial coefficient times theta to the A times 1 minus theta N minus A. Okay? This gives us a PMF, right? Because this quantity, the number of heads, is an uncertain quantity. We're getting the probability of the uncertain quantity having every possible value. So here A can go from 0 to N. So we have a PMF. And you could check that the PMF adds up to 1. I encourage you to check it on your own. This PMF characterizes the binomial distribution, which is a really important distribution. Okay, we say that a random variable has a binomial distribution if its PMF looks like this, and there's two parameters, N and theta. Theta is usually the parameter that we would estimate from data because we're probably going to know N, right? Like something happens N times and we assume that they're independent and they all happen with the same probability. That's a binomial. N we usually know, theta we might want to estimate from the data. This is a binomial with N equals 20 and theta equals to 0.2. This is a binomial, N equals 20, theta equals to 0.5. When theta grows, the larger values of A, with respect to smaller theta, you get more probability towards the larger values. And if theta grows even more, you get even more probability, okay, closer to N. Okay, so that's how the parameter theta affects the shape of the PMF. Okay, but the shape is completely determined by the formula that we have established. It only depends on theta, on that parameter. Now we're going to make a short interlude before we go on to derive another very important discrete distribution, and we're going to see a very interesting application of the binomial distribution, and that is to analyze the empirical probability. So up to now we have been using empirical probabilities all over the place to estimate probabilities from data. And the idea was very simple. You're interested in the probability of a certain event that is in a certain sample space, and you observe some data that can either be in the event or not be in the event, and essentially you estimate the probability of the event using the fraction of data that are in the event, that you observe are in the event. And that's a statistical estimator, which is the empirical probability, and we have seen that sometimes it can be a bit noisy, but we didn't really have any tools to analyze what we meant by that. And now that has changed. Okay, now we have a tool. The binomial distribution is going to allow us to understand how the empirical probability behaves under certain assumptions. Okay, so we're going to, this is what I just said, we're going to analyze the estimator. So let me go on to the next slide. We're going to assume that we have some data that can be modeled as random variables. Okay, like each data point is a random variable. We're going to assume that the probability that the event, the probability that we want to estimate is a certain probability theta true. Okay, that's the probability that we want to estimate. We get to observe some random variables that are equal to 1 or 0. If the random variable is equal to 1, that means that the data point is in the event of interest. And if the random variable is equal to 0, then that means that the data point is not in the event of interest. So now the number of data in A is given by a random variable, which is just, think for a moment what it is. It's the sum of the AIs. Okay, the way we have defined AI is that AI is 1 if the data point is in A and it's 0 otherwise. So if you want to count how many data points are in A, that's just the sum of the AIs. Okay, so far so good. Now we're going to assume that the data are obtained independently, which is a very common assumption. The idea is we're trying to characterize this event. I don't know, coin flips if you want, the probability that a coin flip is going to land on heads or not. And we're going to assume that the data are acquired independently. If I see that a coin flip is heads, then the next coin flip is not going to depend on that. It's only going to depend on the actual probability of heads. This is the assumption that we're making. In order to encode that mathematically, what we're going to assume is that the random variables, the events, because we haven't talked about independence of random variables yet, but we're going to talk about that later. This is kind of, a bit of a sneak preview. The events A1 is equal to 1 or 0, A2 is equal to 1 or 0, up to AN equal to 1 or 0 are all mutually independent. Okay, so here I could put in any ordering of 0, 1, 1, 0, and so on. All of that should be mutually independent. Okay, and that's the assumption under which we're going to analyze the empirical probability estimator. Okay, so now we're interested in the count of the number of data that are in the event, because this will allow us to analyze the empirical probability estimator. So what is the distribution of the number of data points that are in the event under the assumptions that we have made? So just to recap, the assumptions are each data point is in the event independently, and there's a probability theta which is fixed, theta true, that the data point is in the event. Okay, so under those assumptions, this is exactly a binomial. Okay, so, and the parameters of the binomial are n, the number of data points, and theta true, which is the probability of the event. Okay, so this is a PMF that we had derived before. Of course, we're not interested in the count, right? What we're really interested in is in the behavior of the empirical probability. The empirical probability is related to the count. It's just equal to the counts divided by n. Okay, so this is the empirical probability. We're going to call it theta squiggly because it's a random variable that tries to approximate theta true. Okay, that's why I've decided the squiggly is because it's a random variable, the tilde on top. Theta, it's because it's approaching, it's supposed to approximate theta true. Okay, so we know that it's equal to the counts divided by n. So what is its PMF? I like to always go to the definition. What is the value of the PMF of theta tilde at t? It's just the probability that theta tilde is equal to t. Okay, and now I gave up. I showed you the solution a little bit too soon, but the probability that theta is equal to t is equal to, the probability that theta is equal to t is exactly the same as the probability that the count divided by n is equal to t, so it's exactly the same as the probability that the count is equal to nt. Okay, What is the probability that the count is equal to NT? We've seen that the count is a binomial, so we can just plug in the binomial PMF there, putting NT, okay, in the place of A, or well, of the count, basically. Okay, so this gives us the PMF of the empirical probability under these assumptions. And then we can go look at it and see how well the empirical probability estimator approximates the true probability of the event. So you remember when I wanted to show you that the empirical probability is actually quite noisy and you might not get a perfect approximation, or you will always not get a perfect approximation, I had shown you these results where we had simulated a fair coin that has probability 0.5 to land on heads. We had simulated it 20 times. Okay, and we did it, so we had flipped 20 times and we repeated the simulation 10 times. Okay, and in each of the repetitions we see that most of the time the estimate is far from perfect. One time we're lucky in this one. So now we can actually analyze this situation mathematically using the derivation that we just obtained, because we know the distribution of this number under the assumptions that the coin flips are independent and each of them has the same probability. So we can go ahead and plot it. So here I've plotted that distribution for theta true equals to 1/2, which is the fair coin, the fair coin assumption. Like you think the probability of heads is equal to 1/2. And I've plotted it for different number of coin flips, because intuitively, if you have more coin flips, you should approximate the probability better, one would think, right? And we're going to see whether that's the case or not. This is the distribution. So the squares are the distribution where you have n coin flips. The stars are the distribution where you have 40, and the circles are the distribution where you have 80. And indeed, you see that, for example, if we're interested in the probability that we approximate the true probability, with an error of less than 0.1, then, we would be basically interested in what's the probability of being between 0.5 and 0.6, because in this case, the true probability is 0.5, and what we would do is we would basically sum up these values for n equals 20, those values for n equals 80, these values for n equals 40, and these values for n equals 20. And it does seem that for n equals 80, we have the probability is more concentrated around the true value of 0.5. Let's make this precise. Let's actually, compute the probability that the error is below 0.1. Again, for n equals 20, which we would basically do like this and like this, and count the points that are within 0.4 and 0.6. And that probability is 0.7 or 73%. So 73% of the time when I look at the empirical probability estimator, it's the error that I'm making is less than 0.1, as long as the true probability is 0.5. If I look at n equals 40, now I'm adding these stars here. Okay, there it's higher, as was it follows our intuition, right? It's almost 85%. So only 15% of the time I'm going to make an error of more than 0.1 in this case, if I flip 40 coins. If I flip 80 coins, so again, here and here, you can actually see that most of the probability is within that interval. The probability is 94%. Okay, so there's pretty high probability that your error is going to be below 0.1. This illustrates how we can use these distributions not only to fit data to them, and we're going to do that for sure, but also to analyze statistical estimators and understand their potential and limitations. And in particular, here we have used it to understand a bit better that when we are computing empirical probabilities and we observe data that are independent, the more data that we observe, the better our estimate is going to be, and we can make that actually pretty precise. We're going to talk a lot more about this later on. Okay, so now I'm going to motivate another famous discrete distribution with an example that has some real data that we're going to be playing around with. Well, actually, that we already played around with in the previous video, which is this data about the streaks of free throws made by Kevin Durant. So let me remind you, we're interested in modeling the probability that Kevin Durant makes, let's say, 10 free throws in a row without missing, or 5 or 6 or 7. Okay, we want the distribution of that number, of the number of free throws that Kevin Durant is going to make before he misses. Our data were 376 streaks, so each streak is a certain number of free throws that he made without missing, that were obtained from the first 3015 free throws shot by Kevin Durant in the NBA. Okay, so the data looks like this. First he made 2, then he missed, then he made 4, then he missed, and so on. Okay, and this is actually the graph that I showed you at the beginning of this video, where if we just apply the empirical PMF to estimate that distribution, it's pretty noisy. So instead, we can maybe make some assumptions and derive a parametric. By parametric, I mean just a predefined PMF that depends on a small number of parameters. And then we'll see if that gives us a better estimate or not. Okay, so what assumptions can we make here to model the streaks of free throws? I'm going to, suggest a few assumptions. You could come up with your own assumptions, and maybe they would be better. The only way to find out would be to actually check this on the data. So I would suggest assuming that the probability of making each attempt is fixed and equals a certain parameter theta, which, if you go from player to player, that would kind of reflect how good the player is at shooting free throws. My second assumption is basically that all attempts are independent. Maybe you're getting the idea, when we're doing probabilistic modeling, a lot of it is just assuming that stuff is independent. That's just how it is, because it just simplifies the models a lot. And then, of course, we will talk about this later on. You have to be careful, because when you are assuming things are independent, sometimes they're not, and that can bring problems. Anyways, here I would suggest that we model the attempts are independent because it's really going to simplify the model. Okay, so do you think these assumptions are true? The answer is, of course not. Absolutely not. He probably has a higher probability of making free throws when he's well rested. He probably, the attempts are probably not independent, right? Like if he's missing a lot, maybe that gets into his head, or if he's making a lot, he might be very confident. And the attempts might also not be independent because they happen in a particular game where, maybe it's an away game as opposed to a home game. Maybe he's, negotiating his contract, maybe he has some personal issues. This might mean that the free throws that happen around that time are all dependent in a weird way. You could imagine many ways in which these assumptions do not hold. So the assumptions do not hold. The question, however, is, do they allow us to get a better model? We will answer that question in more detail in 1 or 2 videos. Okay. Now we're just going to focus on deriving the PMF that follows from these assumptions. No, the assumptions are not true. Okay, so under these assumptions, what is the probability of a streak of length S? What has to happen to get a streak of length S? He has to make S free throws and then miss 1. Okay, so make 1, make 2, up to S, and then miss another one. Here we have an intersection of events. We are assuming independence. Boom, this factorizes into the product. And now our second assumption comes in. Here we're assuming this is theta, we're assuming this is theta, and so on and so forth, and that this guy is 1 minus theta. Okay, the probability of making or missing is fixed. It's always the same. Okay, so that's it. Basically, we get the probability of him making S free throws in a row is theta to the S times 1 minus theta. And this holds for every S from 0 to infinity. So this gives us a PMF of a discrete random variable that models the length of the streaks. And again, you can go and check that the PMF sums up to 1. Okay, this is what the PMF looks like. This is another sneak preview because we haven't learned how to fit this parameter to the observed data. That's what we're going to do in the next video. But just so that you see, the dots here, the black dots, are what we would get when we fit the empirical PMF to the data. The circles are the distribution that we just derived, which is called a geometric distribution, and it's much smoother. Usually, the geometric distribution is slightly different to the one that we have derived. The way that it's usually explained is, I want to flip a coin until I get a heads. We did the other way around. We said, oh, you flip coins, you get heads, 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 until like you don't get a head anymore. So that's why the parameter here, alpha, is 1 minus theta in the way we derive the model. Okay, so here in the geometric distribution, it's 1 minus theta. And then we said we want to see the probability that we have a free throws and then we miss one. The way that people normally derive the geometric distribution, they say, what's the probability that you have to wait, I don't know, a until you make a free throw? So that's why this is a minus 1 and we had s in our derivation. Okay, so this is the form of the geometric PMF that you will probably encounter in textbooks and in other sources, but it's completely equivalent to what we have derived for our free throw example. This is the geometric distribution for a certain value of the parameter. As in the case of the binomial, it has a certain shape, and the shape changes when we change the parameter. But it's very constrained. Okay, it's always going to have this shape like this. But depending on how we tweaking the parameter gives you different, like it's the same kind of shape, but it varies with the parameter. I hope that made some sense. Okay, so we've derived the binomial distribution, the geometric distribution. We are going to derive one more that is really important and shows up everywhere. And that's the Poisson distribution. Okay. The goal here, the example that we're going to use to derive the Poisson distribution is you want to model the number of earthquakes that happen in San Francisco over 1 year. And Poisson distributions are actually used to model earthquakes. They're also used to model neuronal impulses in neuroscience. We will see in another video that they can also be used to model calls arriving or packets arriving at a router or emails arriving at your email address. It's a very popular model. So what are the assumptions that we're going to make when we want to model the number of earthquakes in San Francisco over 1 year? We're going to assume that the earthquakes are independent, as usual, like a lot of deriving like parametric models or deriving parametric distributions, we just assume independence all over the place. I mean, that's just how we do probabilistic modeling. This one is a bit more interesting. We're going to assume that the probability of an earthquake happening in a period of a small length t is lambda t. Okay, so maybe let me draw a small picture. So this is a year. This is a year. And what we're saying is that if you look, if you zoom in on any interval of that year, and you say, oh, so what's the probability that an earthquake happens here in this very small interval? The probability is going to be given, these are assumption by, it's going to be proportional to the length of the interval and to a certain rate of earthquakes, lambda, which is a parameter. In regions where there's a lot of earthquakes, lambda will be larger. In regions where there are less earthquakes, lambda would be smaller. Okay, in San Francisco, we would have to look at the data and determine what lambda is. Okay, so that's going to be our assumption. And our third assumption is that if we look in here, like if we look at a very, very short interval, the probability of having more than one earthquake is 0. if the interval is very, very small, like if t goes to 0. Okay, we're only going to need for this and this to hold where t is extremely small. So the idea, if you want intuitively, is that these earthquakes can happen at any point with kind of the same probability, so to say. They happen independently, and they depend on this parameter lambda. The more earthquakes, the higher lambda is going to be. Okay, that's kind of the idea. So now, what is the probability of A earthquakes? Okay, here it looks like I misspelled, but no, A is the variable that is the number of earthquakes. I should probably have used another variable. Okay, so our strategy is going to be to discretize the year into n slots. So let me draw a picture. Okay, we have, this is the year, and we're going to cut it up into slots of with 1 over n. Okay, 1 year, we cut it up into n slots. Each slot has width 1 over n. And now we're going to ask what's the probability of having A earthquakes under the assumptions that we have derived. So maybe I'm going to copy this picture because I think it will come in handy. Okay, so we want the probability of A earthquakes. This is the probability of, well, I forgot to say that. We're going to do this thing where we have discretized the year into n slots. We're going to take the limit where n goes to infinity, which means that the slots are infinitely narrow. Okay, that's what we're going to do. But in the meantime, before we take that limit, let's reason about this case where we haven't taken the limit yet. We have this discretized year. We're interested in what's the probability that we get A earthquakes. Okay, so now we have slots. Now we're going to assume that the slots are really, really, really small. Okay, oops, I gave that away. Let me, let's pretend that like I didn't do that. We're going to assume that the slots are very, very, very small. Okay. Then the probability that we see A earthquakes is basically the probability of having A slots with an earthquake and having n minus A slots without an earthquake. Right? I mean, that's basically the probability that we are looking for. We have made a few assumptions. One assumption is that the earthquakes occur independently. So whether there is an earthquake or not in each slot, all of those events are independent. This should ring a bell. Number two, we have made an assumption that in each slot, if the slot is narrow enough, which it is because we're going to take the limit where the slots are arbitrarily narrow, if the slot is narrow enough, the probability that there's an earthquake is lambda t. The probability that there's no earthquake is 1 minus lambda t, because there cannot be more than one if it's super narrow. So now, essentially, we have to compute the probability that we see A earthquakes when the probability of each earthquake is lambda t, and they happen in n slots. What probability is that? That's exactly a binomial with parameters n and lambda t. Okay. Yes, sorry. Lambda t here. It's n and lambda t, but lambda t here is lambda over n. I was quite confused there for a moment. I was a bit perplexed. Because we are taking that the slots are 1 over n. Okay, this t that I was referring to was the width of the slot. That's 1 over n. Okay, so we're good. Okay, so this is a binomial distribution. Now, in order to obtain the probability that we are interested in, we just need to take the limit where n goes to infinity. These slots become arbitrarily narrow. We just expand the binomial coefficient, and we get this. And you have to do a little bit of math, but basically, we're going to use the following results. This guy here, by the definition of Euler's Euler's constant, is e to the minus lambda. Okay, so this part is just e to the minus lambda. And now, if you take this part and factorial divided by these two guys, and you kind of without the lambda. So if you just take this part again, okay, let me third. Okay, there we go. If you just take that part and you expand it out, the numerator is n minus 1, n minus a plus 1, and so on. And down here, you have n minus lambda, n minus lambda, n minus lambda. So here, by the way, okay, this part has been obtained by cancelling out the two factorials. So basically, you have from n to n minus a plus 1, right? Like when you cancel out n factorial and n minus a factorial. And then below, you just have n minus lambda 8 times. Because there's the same number of points and we're taking n to infinity, these guys just all cancel out and go to 1. So in the end, we end up with this expression for the PMF, where a can go from 0 to infinity. So again, here you could also check that you can sum this expression setting a from 0 to infinity, and it would add up to 1. This is a valid PMF. So the PMF of a Poisson random variable that has parameter lambda is equal to this, and the way it's obtained, basically, or a way you can obtain it, is by assuming what I assumed, building a binomial on a discrete grid, and then taking the grid to be arbitrarily fine. And when you do that, boom, you get the Poisson PMF. This is the shape of a Poisson PMF with lambda equals to 10. As we increase lambda, the larger number of events, not of events, but like of earthquakes in this case, have more probability. Okay, so that's why we see that the shape of the PMF shifts to the right as lambda increases. What we have seen, by the way, just, this is a side note, we have seen that the PMF of a binomial with parameters n and theta equals to lambda over n converges to a Poisson. Okay, we were saying, we discretize this, we get like a binomial that has parameters n and theta equals to lambda over n. Okay, we get a binomial like that, and then we take the limit, and in the limit, the probability that we're interested in had a Poisson distribution. This means that the PMFs, as n increases, this binomial PMF becomes more and more similar to the Poisson until the PMF essentially becomes a Poisson in the limit. That is called convergence in distribution, where the PMFs converge like that. We're going to talk more about that later on in the course. But every time you prove a result like that, it's nice to just go and see numerically whether it actually holds. So let's do that. There's an example in convergence in distribution of the convergence in distribution. Let's do that. So here we take a binomial with n equals to 40, and we're going to set lambda. Okay, so here lambda, we're going to set it to be equal to 20. So first we're going to set n equals 40, then n equals 80, then n equals 400. Okay, so that's what we do. And now check out the shape of the PMF, how it changes. And eventually it's not changing so much, even from 80 to 400, it doesn't change that much. And this is a Poisson distribution with lambda equals 20. It's essentially the same already when you take n to 400, you don't even have to take n super, super large. You've already almost converged to a Poisson distribution. So what we have proven actually holds when we look at it numerically, which is always good. Okay, so what have we learned in conclusion? We have learned to derive parametric models by making assumptions often about the independence of something related to the phenomenon of interest. We have learned about four very popular discrete distributions: Bernoulli, binomial, geometric, and Poisson. And in between, when we looked at the binomial, we also realized that we can use tools from probability theory to analyze statistical estimators and understand under what conditions they're going to work or not. Thank you very much.